Hi and welcome back everybody to the Realist live coding channel on YouTube, where we make real mistakes in real code, we produce real stuff, we discuss stuff in the comments, and in the end we succeed writing something cool. In the last episode we have coded a timer that interacts with the kernel based on signals, and I want to improve this timer today with your comments, because actually I messed this timer up completely. Or well, not completely, it's working, but it's consuming 100% of the CPU. And what timer is supposed to be consuming 100% of the CPU? Well, no timer is supposed to do that, because timers are most of the time idle. Yeah, imagine you have a CPU with 4 cores and you have one timer running, a 5-minute timer, while you're cooking your eggs, and that timer is eating all your CPU and consuming real energy. So that's completely stupid. Why is it doing that? It's doing that because I have a while loop here, which is busy looping all the time. And of course, I only know that, well, I assumed that's the case, but someone explicitly pointed it out in the comments, of course. But I want to show you the timer in action again. So we have this timer, we specify a time in seconds, and then it's starting to count down. 10 seconds, remaining 9, 8, etc. 7, 6, 5, 4, 3, 2, 1, and now the timer is elapsed. So that was 10 seconds. Okay, and my goal for this video is to not have the timer consume all of the CPU. Because in the comments, someone pointed out, a frequent commenter, by the way, Marek Knapek, pointed out your loop will eat 100% of a single CPU. I would recommend a different method of waiting for an event. He recommends to use timer FD, which we're not going to do, but we're going to do, because that would require refactoring all of the code. But I'm going to solve that by not busy looping all the time. I don't want to run all my CPU in this while loop here. And of course, someone else also pointed out, you do not assign the parse seconds. With your code, you are firing up the signal every second and setting elapsed to 0 in the while loop, which is busy looping all the time. Maybe this is intentional, blah, blah, blah. I answered, no. We don't want to consume CPU unnecessarily. Right, and the solution for that is we have to send the thread to sleep. So currently what this program is doing is there's a main method. It takes as argument the seconds. Then the seconds are parsed from the provided input argument. Then it prints out that the timer is starting. Then it defines the interval, 1 second interval, at which the timer is repeatedly firing events. And then we define a signal action that we associate with that signal. So wait, we're defining the interval, we are setting a timer, a real clock timer based on that interval, and then this timer fires the sig alarm event, and whenever the sig alarm event occurs, we want to execute this action down here, and this action is basically just a this specifies that we want to react to the sig alarm, and we want to execute the action defined in the act structure up here. And on that structure, we define a signal handler. And the signal handler is that method reference up here. And that method reference up here sets a variable elapsed to 1. So whenever elapsed is 1, that means the signal has been fired, and we printf something, and we print the time and set elapsed back to we print the remaining time and then set elapsed back to 0. So then we keep looping until elapsed is 1 again, and then we enter the if case. So whenever the signal whenever the signal sets the elapsed to 1, we enter the printout for remaining time. Of course, that's completely a waste of CPU. So what's the proper solution? I found that we can use, well, if we look up the signal library, probably down here there's a reference to sigaction, which defines what we want to do when a signal is triggered. But there should also be a sigwait somewhere. And I think there's no reference down here, but this exists. Sigwait. And this is a function that waits for a signal. And the sigwait function suspends the execution of the calling thread until one of the signals specified in the signal set becomes pending. The signal accepts the signal. No, the function accepts the signal and returns the signal number in sig. Okay. So what this is doing is it's waiting for a signal and not consuming CPU power. So this is a real energy saver. This is also a real money saver. You don't need to dedicate a complete CPU to the timer process. So let's see if we can fix our code with the sigwait thing. It's already included in signal.h, which we already have included up here. So now we just properly have to include it in our source code. So instead of looping over, instead of looping over until the countdown seconds are 0, maybe we should loop until, or as long the countdown is active. And that is true at first. So while the countdown is active, we wait for a signal, sigwait, and we wait for the signal set. The sigset is, what is sigset again? Sigset. I remember we encountered that structure before, or that variable type. Sigwait, sigset. Maybe we can find some info under sigwait info. So let's look up sigwait info. And this also contains the sigset. So maybe this contains an explanation what sigset is even supposed to do here. No. So let's look up online. What is sigset _t? Signal set. All of the signal blocking functions use a data structure called signal to specify what signals are affected. Okay. Thus, every activity involves 2 stages, creating the signal set and then passing it as an argument to a library function. Data type sigset _t. The sigset t data type is used to represent a signal set. Internally, it may be implemented as either an integer or structure type. Okay, so is it now an integer or is it a structure type? There are 2 ways to initialize a signal set. You can initially specify it to be empty with sigEmptySet and then add specified signals individually, or you can specify it to be full with sigfillSet. and then delete specified signals individually. Okay. You must always initialize the signal set with one of these two functions before using it in any other way. Don't try to set all the signals explicitly, because the sigset object might include some other information that needs to be initialized as well. Aha, so we should only use a function to initialize it. But what do we even need it for? I mean, my understanding was that sigwait, in sigwait you need, or my function, my understanding of sigwait would be, there's the sigwait function. We specify in a single argument that we want to wait for the signal alarm, and that should be sufficient, no? Because then the kernel would know that this process with this ID, the kernelly executing process, waits for a signal with the following ID. Or with the following, with the ID, signal alarm. So I would think that signal here is sufficient. So I don't really get the difference between sigset and the integer signal, because the signal set sounds to me like a set of signals, while the integer signal sounds to me like a single signal that we listen for. So I think we need to research some more. Maybe if what happens if I search the man page of sigset? Oh, there is something here. Sigset. Let's see. But that's about a function that's called sigset. But maybe it's related. Okay, looking up sigset_t also yields some results. This is a type that represents a set of signals. Okay, so we represent a set of signals, but then we also represent a single signal via its ID, integer. Which is what I don't exactly get so far. According to POSIX, this shall be an integer or structure type. Well, so it's very generic. Is a type that represents a set of signals. Sigwait. Sigwait returns only the signal number rather than siginfo, blah, blah, blah. Maybe we can wait for either a set or a specific or a single signal. The sigwait function suspends execution of the calling thread until one of the signals specified in the signal set becomes pending. The function accepts the signal, removes it from the pending list of signals, and returns the signal number in sig. Okay. I get it now. So here we specify the signals that we are waiting for, and the result signal that has unblocked our signal wait is then entered into this signal variable here, which is passed via a pointer. And that's one thing that I frequently find annoying about the API in the C language. somehow frequently the return value here, or well, a return value is, no, let me start again. Frequently the positional arguments here, or the arguments to a function, are used as return values, which I find kind of confusing, but for sure there's a reason. But in other languages, such as in Java or Python or whatever, JavaScript or so, that's a bad practice, because there we enter stuff into a function, we enter arguments, and then the return value is this. But in C, it's this function return value is often an error code, while the produced result is entered via the argument, which is input as a pointer, such that the method can access that memory space here. And that's what I find kind of confusing. And sometimes this is the real return value in a function is an error code, but sometimes it's also the case that the return value, the produced return value, is entered in this positional argument memory location here, but then also returned via the function's return value. So it's returned in two places. It's kind of interesting. There's for sure a reason. Yeah, and here the reason is that the return value is a success signaling value. So on success, sigwait returns 0. On error, it returns a positive error number. Yeah, so I think the core reason why C is doing that is that actually this is the best way to do it. In other languages, if this function yielded an error, then it would throw an exception. But in C, there's no such thing as an exception. So any error is signaled via the return value of the method. And the produced result is then put in a positional argument here. In a function argument. It might be different from a positional argument. Yeah, I think this is a function argument, and a positional argument is something, is an argument that is passed, for example, to a program that you execute in the terminal, where its meaning is determined by the position, but here it's also determined by the data type. Yeah, function argument. All right. So now I talked so much that I almost forgot what we were even doing. So what we have to do is we have to specify a sigset. And sigset almost sounds like success, which is what we are after here. Sigset underscore t. And we have to create I think we should create an empty sigset. Sigset underscore t empty. Oh, we just saw some documentation somewhere that told us to never create this structure, the sigset structure, manually. But what again is the function used to create it? There's no instruction to create the sigset. According to POSIX, this shall be an integer or structure type. So if we look here, here it said that we can use sigEmptySet to initialize a sigset. Yeah. And the method expects as input sigset. Wait. Okay, no, I have to give it a pointer as that's again the same thing. Here I thought this method creates for us a sigset, and we have to pass a signal integer as an argument, but actually it expects the sigset t as an argument, which is the snake biting its own tail. It's a recursion, because I thought we need to use the sigset underscore t, no, the sig empty set function to create a sigset t, but it expects a sigset t as an input. So because we don't have a starting sigset t, we can never create a sigset. What the hell am I doing with my life here? But this is the same thing. It's, again, an error code as a return value, and this right here is a pointer which is filled with the actual method, with the actual value that the method yields or creates. So we will use the sig empty set. Let's create the sig empty set. Or it would be even funnier if it just worked with sig alarm. And all the sigset discussion would have been unnecessary. So let's try to no. We have to wait for a proper sigset. I'm not going to do that. We have learned about the sigset concept, so we have to use it. Sig empty set, I think, was the method. Yes, sig empty set. And let's initialize the sigset t here. Signal to wait for is equal to, and we have to, do we have to allocate the memory using malloc? No, I don't think so. I think we can leave it on the stack. No, so that's the signal to wait for, and now we want to fill that value with something. And we do that using sig empty set. Then we pass the address of signal to wait for. And now we should have a filled value. We can, of course, also check the return value. Success. Or we can also use this in an if case directly. So if this is 0, it's a success, but if it's not, then we can print that we encountered an error to the console. Printf encountered an error defining or creating the signal to wait for. And then we pass the error code, new line, and the error code, oh, we don't know the error code because I haven't stored it in a variable. Yeah, then let's omit the error code for now. I'm not expecting an error anyways. And then we can exit the application here. And now the next step is to now we have initialized the signal to wait for. Now we would have to, of course, in sigwait, use that signal to wait for. And I think we can remove the if case now and the elapsed variable. So now the sigwait should just wait and do nothing until the signal is encountered. Then we print out the remaining time. The remaining time is countdown seconds, and then we decrement it, or we decrement it and then we print it out, which is something that another person also pointed out in the comments here. Wait, where was that? You should have used countdown seconds minus minus instead of minus minus countdown seconds. The way you did is always going to count 1 second less. Okay, so let's just fix this as well. And we can remove the elapsed global variable, and I think now we have a while loop. We still have a while loop, of course, because we want to loop while the countdown is active. And from there, we keep counting down, but we don't consume CPU time because sigwait is sending the thread to sleep. It suspends the execution of the calling thread, which saves our CPU. So let's see. I would like actually to save the old timer binary. So let's move it to CPU hungry timer. And then we create the new timer using GCC, output timer. Input is timer.c, and input arguments are WALL, WXOR to enable all the warnings, and debug flags as well. And of course, it doesn't work. And later I want to compare the new timer that we generated with the CPU hungry timer that we created in the last episode. So here, elapsed is undeclared, first use in this function. Yeah, okay. So where's elapsed used? Elapsed. In the signal handler. Of course, do we even need a signal handler now? Technically, we don't even need the signal handler anymore because sigwait is waiting for the signal, and probably we can remove this signal handler. Let's see, can we just remove it? No, we can just define that we can just say that we don't want to execute any sig action. Oh, this would be much better, because now we're just telling the code to fire signals, and we wait for signals down here and do something. So even the sig action is unnecessary now. That would be a big improvement in the simplicity of the code. Let's see. So the signal to wait for incompatible type for argument 1 of sigwait. Signal to wait for must be a sigset pointer, probably. Yeah, expected constant sigset pointer. Then let's give it a constant sigset pointer. That's it. And let's see what happens now. That error is gone. Now there's still an error. Too few arguments to function sigwait. Of course, we have to pass this a signal variable, an integer. And that must be a pointer as well. I don't know, is there a good way in C to just give this sigwait or any function that requires an integer pointer just a dummy variable? Can I just say null here? Because I don't need that value. Maybe I can just say null. Because I don't need to track the actual signal integer that caused the suspended thread to become pending again. All right, argument 2 is null where non-null is expected. Okay, so it can't be null. Yeah, damn it. Then let's give it this integer value, but if anyone has a good idea how we can give this dummy values, that would be very nice, because I don't want to create variables for stuff where they might not even be necessary. Well, it needn't be a dummy value, but maybe some memory where we can just write stuff into which we don't need anywhere, anytime. But if this is a bad practice, then also just let me know. Did I save this? Oops. Cannot wait, what's that? Okay, now it compiled without any issues. And I would say let's rename the timer to efficient timer. And let's remove the old timer. Now we have from the last episode the CPU hungry timer, and from today's episode the efficient timer. So let's see how they differ. The CPU hungry timer, of course, well, I think from appearance they will barely differ. Let's see. Starting timer of 3 seconds, remaining 210, timer elapsed. The efficient timer should look very similar. Ah, no, there's the alarm clock issue. That's something that we encountered also. In the last episode. So we have to give this a signal handler, otherwise some default handler will be used, but our signal handler can be zero or can be meaningless because we have to override the default action. At least that's my understanding. So we give this a signal handler. The signal handler, I have to look up the Git history, how that signal handler was defined. No arguments here. Okay. Signal handler does nothing. And down here we wait and print something to the console. Actually, we can also print in the signal handler. It doesn't really make a difference at all. No, let's keep the signal handler empty. But probably instead of defining an empty signal handler, there's also a better way to do that. To suspend the signal's action, there's probably something like signal ignore or something. I think I saw something like that. Signal interrupt, signal queue. What can we see here? Sig ignore. There's a sig ignore. No, but I don't want to ignore the signal. I just don't want to execute an action. Well, or I want to execute an action, but it needn't be defined in the signal handler. So we can let's keep this in the empty signal handler. Or we do use printf instead inside this signal handler. Signal handler remaining seconds flush. Here we wait. Then the countdown is still active, so we keep waiting. Then the countdown is still active, and we keep waiting. And one more point is we have to check, of course, if the countdown seconds are 0. So there are no remaining seconds. If they are 0, let's say smaller than or equal to 0, just to be safe. I read this is a best practice somewhere, but actually it will never become smaller than or equal to 0 if we properly suspend or exit the application. And then we do exit. Then we have counted down to 0. No, let's not exit. No. We don't exit. We set countdown active to false. Okay, now it might be good. So do I have to fix up stuff again? I'm waiting for the signal to wait for. And in sigwait, of course, we need to signal value here. We need to provide the signal value here, which we have done before as well, but we have undone it, or I have undone it. Signal to wait for must be a pointer as well. And then we should be good to go. Okay, now it compiles without any warnings. That's a very good sign. So let's I just want to split this pane. And now move this pane here. Clean it up. And now we can run the timer and see if it works. Let's see. So we have two timers again, the efficient timer and the CPU hungry timer. Now let's start with the CPU hungry timer, 3 seconds. Okay, that one worked. And then we have the efficient timer. Did I even create that properly? Yes, I did. Okay, efficient timer 3. Right, and this one doesn't stop. Why doesn't this one stop? If countdown active must be 0, of course. Right, let's try again. What? Wait, I just set, didn't I just set countdown this to countdown active? I just renamed it. Okay, let's try again. What the hell? Why is it not exiting the loop? Countdown active is set to 0 here. If the countdown seconds is smaller than or equal to 0, it's time to jump into the debugger. So let's go into GDB, efficient. Do I have even GDB installed here? Yes, I do have it. So let's GDB efficient timer layout next and see break in line. We want to break in line, let's say 54. And let's run this with 3 as an argument. I hope this, yeah, did work. But somehow it just counts down and doesn't even reach the breakpoint. Why is that? I did put a breakpoint, didn't I? What if we break in line 53? Maybe we are waiting for the wrong signal. Did I even specify the signal to wait for? Sigwait, signal to wait for. the signal to wait for is in sig empty set. Oh damn, I forgot specifying the signal to wait for. Oh god. So how can we add a signal to this empty set? We can use sig add set and add a signal number to the set. So we have to add our signal there. Okay. Sig add set, and let's just remove all this error handling. I mean, if we use all the code properly, then there won't be any errors. I want to keep it concise for this YouTube video. Sig add set, and we want to add to signal to wait for. We want to add sig alarm. Okay, and now it's compiled, and let's see what the efficient timer does. And by the way, why did it work before? Because the signal was sent, and every time the signal was received, well, while this was waiting for no signal at all, and it was blocking all the time, the signal handler up here was printing whenever a signal was being sent. So the signal handler was executing, but this wait function was not. Then we could even further simplify the code probably. Oh god. Okay. I think now it should work though. No, it's not even doing anything. Why? Let's run the efficient timer for 3 seconds. It's not doing anything. Why is it not doing anything? Maybe now the signal handler and the sigwait are somehow interfering. What if I don't know, by the way. This is just a guess. Or no, I keep the signal handler as it is, but I do the following. I printf here received to notify us that we have received the signal. And here we write waiting. Let's see what happens now. So we are waiting, receive, waiting, receive, waiting, receive. So that seems to work. But now the signal handler doesn't run. Why does the signal handler... Why is it empty? Now it's not empty anymore. But if I compile now, it doesn't print stuff. And maybe that's because the printf interferes. Printf waiting. And here we printf received. Again. Waiting, received, waiting, received. So the signal waiting and the signal sending, they work, but in the signal handler, the printf doesn't seem to work. And I think I read somewhere that we shouldn't use printf in the signal handling. Printf signal handler. Since printf is not re-entrant, it's not supposed to be safe to use in a signal handler. But I've seen lots of example codes that use printf this way. Blah, blah, blah. Okay, so this seems to be somehow discouraged. So maybe instead of doing discouraged stuff, let's get our print out and paste it where we need it, right here. And in the signal handler, we can instead, let's just simplify this a bit. Here we just print the remaining countdown, but whenever the signal is received, such that the signal handler is not jobless, its job is to decrement the countdown seconds. And now let's remove this, and now we should be good to go. 3, 2, no. So it seems that the signal handler is for some reason not executing at all. I have the suspicion that the signal handler is somehow interfering with the sigwait. I just can't prove it. Signal to wait for, signal value. What is the signal to wait for? The signal to wait for is this. And we add the sig alarm to it. So that seems to work. Why does the signal handler not do anything? Signal handler doesn't work. Any shared variables used in signal handlers should be set as volatile. Wait, is this even C? Is this Java? No, it's C. Volatile. Okay. Okay. Volatile. That volatile means, as far as I know, that whenever a value is set, it is immediately available to all threads. But this doesn't seem to change the behavior. Your signal handler has undefined behavior as a result of its call to printf. In the event that the signal handler is ever triggered, that gives the whole program undefined behavior, which makes it very difficult to reason about its observed behavior. Yeah. But I mean, I'm just decrementing a variable that should be safe to do. But C programming is really a pain in the ass. Your code invokes undefined behavior because it calls a function that isn't async signal safe. Signal handler countdown seconds minus. Does it change if we do minus countdown seconds? No, of course not. But then what's the issue? Why is it stuck at 3? We wait for the signal, we printf something, we flush. We don't need a signal handler. I would actually like to remove the entire signal handler, but then the signal would cause this default action with the alarm. Sig action, man, sig action. If act is non-null, the new action for signal signum is installed from act. But we can set it to null. That means we can just set it to null. So let's remove all of that, set this to null, and get rid of the damn sig action, default sig action stuff. I don't need any of that. I just want to wait for the signal. But now we have this default alarm clock. What if I remove the sig action entirely? That's crazy. So we need our own signal handler, but why can it not decrement countdown seconds? Let's compile this and see if we ever enter the signal handler function. So here, quit this. Let's GDB this, layout source. And then let's put a breakpoint in line 10. Break 10. Run for 3 seconds. And it seems like we're not entering the breakpoint. We're stuck at remaining 3 seconds. Why? We wait for a signal, we printf something to the console, we flush, we check is the countdown now smaller than 0? And if so, then we set countdown active. We could even simplify that. Why? While countdown seconds are bigger than 0, we loop. But that shouldn't change the behavior of the code so much. It just gets rid of a single variable. Sigwait and sighandler, I feel like they both don't like each other so much, because one is waiting for a signal and then unblocking the current thread, and the other one is in parallel changing something in that same thread. Sig action, sig wait. So far, I've used sig action to call a signal handler that uses a semaphore to let the main and other threads know it's time for shutdown. The reason for using semaphores is that semaphores are async signals safe. Blah blah blah. C, ignore signal? No, but we can't ignore the signal. Somehow the actions are contradictory. Signal waits for a signal. And I think the signal handler somehow captures that signal. Here we have a signal handler which counts down seconds whenever the signal is encountered. Then we wait for the signal down here. But if we decrement here, then everything works fine. It seems like a signal handler is set, but somehow it's not really invoked. Sig action. So maybe we have to check sig action again. Sig action. And this also expects an SA mask, which we have deleted in the last episode. Specifies a mask of signals which should be blocked, added to the signal mask of the thread in which the signal handler is invoked during execution of the signal handler. This is a signal handler mask. No, wait. In addition, the signal which triggered the handler will be blocked until the SA no defer flag is used. Specifies a mask of signals which should be blocked. What does that mean? Added to the signal mask of the thread during the execution of the signal handler. Can it be null? I don't think so. We need to probably specify an SA mask as well. Act SA mask is and let's fill that somewhere here. And the mask is sig empty set action or address of action SA mask. So here we specify that we want to not ignore any signals during the execution of the signal handler. That's my understanding. So maybe that's what is missing. Let's try again. And let's remove the decrementing here because I actually want the signal handler to decrement. But that doesn't work. C signal handler is not executed. Actually, the entire reason why we have the signal handler is because I don't want to have the default signal handler. Default signal handler is somehow canceling the process and printing alarm to the console. Signal ignore default action or something like that. I'm just removing the entire signal action thing because this is just confusing. It's like we're doing the same thing twice. First, we have a command handler, which we don't need, and then we sigwait for something. The sigwait is also like a command handler already. So whenever the waiting period is over, we decrement and then count down. But now alarm clock is being printed to the console. Let's ask grok.com. And let me copy the entire command. Let me copy the entire source code using xclip selection clip, I think like this, to the clipboard. Because of a critical bug in how you're using sigwait together with setITimer. Sig alarm's default action is to terminate the process. Yeah, that's what I was thinking. You're calling sigwait, which does consume the signal safely, but only if the signal is blocked first. You never block sig alarm. Sigwait only works correctly when the signals you're waiting for are blocked in the calling thread. But if the signal is blocked, then how can sigwait get the signal? If sig alarm is not blocked, when the timer fires, sig alarm is delivered to the process. Since no handler is installed and it's not blocked, the default action runs. Process is killed with alarm clock. Sigwait never gets a chance to see it. Block sig alarm before arming the timer. What is this doing? This is using the function sigprocmask. Many people find sigwait overkill for simple countdowns. A simpler and very common way would be to use the handler. Yeah, fine. But that's what we did before, right? And we can use pause to just wait for the next signal, it seems. Wait, what is pause doing? Wait for a signal. Causes the calling process to sleep until a signal is delivered that either terminates the process or causes the invocation of a signal catching function. Oh, that's a nice one. But how does it compare to sigwait now? What if we search for block here? There's no mention of the term block. So how am I supposed to know that just looking at the manual? But how can sigwait see the signal if we block it before? Doesn't the blocking block the signal from reaching my process? Blocking does not prevent the signal from being delivered to the process. It only prevents it from being handled by the default action or a signal handler. It only prevents it from being handled by the default action or a signal handler. The kernel still generates and queues the signal. Signal becomes pending. Sigwait removes it from the pending queue and returns it to you safely. From man to sigwait, signals in set must be blocked. Wait, I just looked up man to sigwait. Ah no, I looked up man sigwait. But here nobody says block. Do I have faulty man pages? Sigwait man page. I'm looking up sig3. What's the difference again? Let's look up man. 2 is system calls and 3 is library calls. But what about sigwait 2? Oh, and there's a mention of block. This is unreadable. Sigwait 2. The signal specified by set should be blocked but not ignored at the time of the call to sigwait. Okay, so here this tells us that we have to block the call. And what does this also references pause? Does this mention pause in the text? No, it doesn't. Should be blocked. Okay, block signal in C. Sigprocmask function to block signal. Sigprocmask. Examine and change blocked signals. So we use sigprocmask. Integer how? What's that? We want to block, of course. So let's do that. Let's do that. So this is preparing the waiting, but we have to block signal before waiting. Sigprocmask, and we have to sigblock, and specify another set, a sigset. sigset t. Now we're pros at at specifying all of that. Block set, and block set is sig empty set. Specify the address of block set here. Block set. Which signal do we want to block? We want to sig add set. We want to add sig alarm to the block set. Recall the syntax as such. And now the last argument is the old set, which we don't need. So probably we can keep it null. Let's try. That doesn't work. What's the warning and error here? Sig alarm seems to be invalid. Sig add set makes pointer from integer without a cast. Sig add set. We have to look up the manual for sig add set. Sig add set. We add to the set an integer. So it's the reversed way. So to the block set, we add sig alarm. Let's see what the compiler tells us now. And this error has faded away. And now the block set must be a pointer, of course. And now let's see. Now it compiles. Efficient timer 3. And it works. And yeah, we are now successfully waiting for the signal. We have blocked the signal before waiting. Specify the waiting. Signal to wait for. But actually we don't need that anymore because the signal to wait for is the same signal that we block. Oh, so we can do the following. We can say that the signal to wait for is the signal that we block. Then we can remove all those calls to the block set thing. And we can block the signal before waiting, just like this, and then use the same signal specification to wait for that. So instead of using block set, let's use the signal to wait for here, and let's go. 3, 2, 1, 0. I don't like that it's starting the timer of 3 seconds here. I want to print out only the remaining time. How do I do that? I can probably just remove this starting timer print out statement. And let's check it now. And now I want it to start with 3, of course. So the solution would be it wouldn't be, I think, to append, to decrement postfix here, as one of you commented, because this would wait a total for 4 seconds. Oh, wait, what's that now? That's somehow wrong. While count on seconds is bigger than or equal to 0, of course. Let's try again. So the issue with this code is, in my opinion, that it waits currently for 1 second before it's printing anything. So actually it's waiting 4 seconds now. So we want to wait after the printf. And then maybe count on postfix. Let's try what this does. 3, 2. Oh no, this seems to work now. Ah, yeah, that is okay. It is the postfix countdown, of course. 3, 2, 1. Perfect. Okay, and now comes the interesting part. Since we've learned so much again today. That's awesome. Let's do the interesting part, and the interesting part is CPU, system monitor. So let's run the efficient timer and the inefficient, both of them, and see how they compare in their CPU consumption. Well, what is maybe one important or one useful command that can help us here is the time command, which specifies how much time a program runs and also how much system resources it used. So let's try with the time command first. So first let's run the CPU hungry timer for 3 seconds. And it used, this is the real time that it took from start to finish, as far as I know. Let's look up the documentation again. Right, elapsed real is the wall clock time used by the process in hours, minutes, seconds. And however, the user time, that's the number of CPU seconds that the process used directly. So that's how much time the CPU ran at full throttle in this process. That's how much time was the CPU active and dedicated to just this process. So, CPU hungry timer, let's make it 5 seconds, and you will see that the CPU will run for very close to 5 seconds. As you can see, yeah. This is how much CPU time it took. So running the timer for 5 seconds consumes 5 seconds of CPU time. By the way, for multi-threaded applications, if you have something that is hugely parallelized, there you will see that the user time will be bigger than the real time because there multiple CPUs will be running at the same time. So the CPU times of the individual cores, they will add up. Okay, so the CPU hungry timer is very inefficient, as you can see. I would also like to run it and have a look at the system monitor, and let's see the CPU usage here going up for CPU 10. I think that's probably the CPU dedicated to the timer process, and now the timer process is done and CPU 10 is going down again. So we have a timer task and it's really consuming an entire CPU here. That's crazy, isn't it? Maybe I should make it even a bit bigger. So now you can see the CPU here much better. Let me run it again. The CPU hungry timer is consuming, or is really spiking, a real CPU here. So this is really causing something to go up. Of course, this right here is displaying real CPU usage, and this right here is displaying a virtual CPU. So probably that's why you don't see it going to 100% exactly and then going down again. I think this doesn't map to the real CPU 1-to-1. But you can see the timer takes up energy, definitely. If we run instead the efficient timer, let's try the time command, efficient timer. Let's see how much CPU time this one consumes. So let's start it with 5 seconds first and see how much time it consumes, how much CPU time it consumes. Yeah, and this is incredible. This is an incredible result. So the real time this ran is 6 seconds actually. So there's a bug in the code. Yeah, it's because of that countdown seconds. Because we're counting down from 5 inclusive to 0 inclusive, and that's 6 seconds. But actually, that's the nicest display of the time that is elapsed, because you display the full first seconds and the full first second, and then also the full last second. Well, maybe we can omit the full last second. So let's do this and compile and check the efficiency again. And now we should see that we consume almost exactly 5 seconds of real time. And the CPU consumes no time at all, or practically no time. It must be in the nanoseconds or microseconds range. And that's the efficiency gain you get from this. So basically this timer does not cost us any energy. And this is why it's so important to know what you're doing. Yesterday in the last video, I was coding this timer, and I, of course, I was dealing with the signals for the first time ever, but today we learned how to properly do it such that we don't consume CPU. And this is now, of course, a radical improvement. So let's run the timer again for 10 seconds and let's switch to the CPU monitor. And as you can see, there's now no CPU spiking. And this is a huge improvement. Again, let's check out for comparison the other CPU hungry timer. And as you can see, a CPU is spiking up. And this is the result that we achieved in this episode, guys. We coded 2 variants of a timer, one timer in the last episode and one improved timer today. And today's timer does not consume any CPU at all, except for a fraction of a microsecond maybe. And I love that result. I love efficient stuff. I love when things go smoothly and when things just work properly. And so thank you guys for your comments. Thanks to them, I learned something. And if you want to give back, then leave a like and subscribe. And check out my Patreon if you want to support me. But aside from that, just keep coming back and watch this stuff and have fun with me. All right, see you next time. Bye-bye.